This is a video from section 11.3. We're going to look at the following. For what values of p does the series from n equal 1 to infinity of 1 over n to the p converge? We're going to break this up into pieces. Let's assume p equals 1. And so we're going to let f of x equal 1 over x on 1 to infinity. First, f is positive on 1 to infinity. So we're going to apply the integral test here. F is continuous on 1 to infinity. And third, we want to verify that f is decreasing. And to do that, we need to look at f prime of x, which is equal to negative 1 over x squared. And f prime of x is less than 0 on 1 to infinity, which tells me f is decreasing on 1 to infinity. So the integral test applies because we looked at all three conditions. Now, the integral from 1 to infinity of 1 over x dx is equal to the limit as L goes to infinity of the integral from 1 to L of 1 over x dx. But this is the limit as L goes to infinity of natural log of x evaluated from 1 to L. And so this is the limit as L goes to infinity of natural log of L, and this is equal to infinity. So what that tells me is that the integral from 1 to infinity of 1 over x dx diverges. And so therefore, this series from n equal 1 to infinity of 1 over n to the p diverges for p equal to 1, and this is by the integral test. So this is the classic application of the integral test. From here, we're going to assume p is greater than 1. So same game, we're going to let f of x equal 1 over x to the p on 1 to infinity. F is positive on 1 to infinity. F is continuous on 1 to infinity. The derivative, so in other words, f prime of x is negative px to the negative p minus 1. But this is negative p over x to the p plus 1, which is most certainly less than 0 on 1 to infinity. And so, therefore, f is decreasing on 1 to infinity. Okay? So, from here, the integral test applies. And so, the integral from 1 to infinity of 1 over x to the p dx is the limit as L goes to infinity of the integral from 1 to L of x to the negative p dx. Right? And so this is the limit as L goes to infinity of x to the 1 minus p divided by 1 minus p evaluated from 1 to L. And remember, this is x equal 1 to x equal L, to remind ourselves where we're plugging in to. And so this is the limit as L goes to infinity of L to the 1 minus p over 1 minus p minus 1 over 1 minus p. Now, let's make sure we're okay here. Remember, we assumed that p is greater than 1. And so 1 minus p is less than 0. Okay? And so one way we can think about this is if I take L to the 1 minus p divided by 1 minus p, can we agree that this is 1 over, and then this is 1 minus p, and this is L to the p minus 1. So that's a property of exponents. And remember, if we have p minus 1, if p is greater than 1, p minus 1 is positive, right? And so as L gets large, this is going to 0. And that's why this first term goes to 0. And then what we're left with is negative 1 over 1 minus p. But what does that mean? What that means is the integral from 1 to infinity of 1 over x to the p dx converges for p greater than 1. And so the summation from n equal 1 to infinity of 1 over n to the p converges for p greater than 1. Again, this is by the integral test. Okay? Now, assume p is between 0 and 1, right? So in other words, assume p is greater than 0, less than 1. And we're going to let f of x equal 1 over x to the p on 1 to infinity. Same three conditions, right? F is continuous and positive, right, on 1 to infinity. That does not change. F prime of x is equal to negative p over x to the p plus 1, which is less than 0 on 1 to infinity, and so therefore f is decreasing on 1 to infinity. The integral test will once again apply. And so the integral from 1 to infinity of 1 over x to the p dx is equal to the limit as L goes to infinity of the integral from 1 to L of 1 over x to the p dx. And so this is the limit as L goes to infinity of the integral from 1 to L of x to the negative p dx. And so this is the limit as L goes to infinity of x to the 1 minus p divided by 1 minus p. Evaluated, again, I want to remind you, from x equal 1 to x equal L. Okay? From here, this is the limit as L goes to infinity of L to the 1 minus p divided by 1 minus p minus 1 over 1 minus p. Now here's the twist. This is equal to infinity. Why? Because if we look at the exponent on the L of that 1 minus p, it turns out that 1 minus p is positive if we assume p is between 0 and 1. And so the integral from 1 to infinity of 1 over x to the p dx diverges for p between 0 and 1. So for p greater than 0, less than 1. So the summation from n equal 1 to infinity of 1 over n to the p diverges for p greater than 0, less than 1 by the integral test. It's a tremendous problem. I know it's a bit lengthy, but I'll show you why this is so nice shortly. Now, if p is less than or equal to 0, it turns out that the summation or the sum from n equal 1 to infinity of 1 over n to the p, that's going to diverge by the test for divergence. Does that make sense? So if you notice, the limit as n goes to infinity of 1 over n to the p is the limit as n goes to infinity of n to the negative p, right? And this doesn't equal 0 if p is less than or equal to 0. Because if p is less than or equal to 0, negative p is greater than or equal to 0. So that's not 0. And if that's not 0, that series will diverge by the test for divergence. And we can sum this up as follows. And it's called the p-series test. So we're down here. So the summation from n equal 1 to infinity of 1 over n to the p converges if p is greater than 1 and diverges if p is less than or equal to 1. That is a nice result. And I want to give you a couple of quick examples here. If I give the summation from n equal 1 to infinity of 1 over n to the 5 halves, doesn't matter, right? This is all you have to say. P equals 5 halves, which is greater than 1. Therefore, the summation from n equal 1 to infinity of 1 over n to the 5 halves converges by the p-series test. Or converges by p-series. That's fine. That's it. Example 2. If I give you the summation from n equal 1 to infinity of 1 over n to the 0.9, okay? P equals 0.9, which is less than or equal to 1. And so, therefore, what do we know about this series? Well, it turns out that the summation from n equal 1 to infinity of 1 over n to the 0.9 diverges by p-series test. You're done immediately. So on problems like this, we don't necessarily have to do the integral test. Can you do the integral test on these two examples? Yes, you can, but you don't have to. So, okay, that'll conclude this video for section 11.3. We looked at the p-series test and did a couple of examples. Thank you.